today's chief guest and head department of chemistry, Professor K. Pramila Madam, and convener D. Koteshwar Rao for inviting me for this lecture. I'm grateful for the opportunity to deliver the extension lecture. So today's topic is exploring natural products from fundamental concepts to therapeutic applications. So here, the importance of the natural products. Natural products have been the foundation of medicine for centuries, and from traditional remedies to modern drug discovery, and they bridge chemistry, biology, and also the pharmacology. So coming to the importance of natural products in our daily life, there are many applications. And if you see the best example, we obtain curcumin from the turmeric, which is the antibiotic drug, and also the morphine obtained from the Papaver somniferum. It is called gasagasalu in Telugu, which is a very good analgesic, and also the theonine obtained from the tea plant, which is which improves the brain functioning. And the other drugs from ashwagandha roots, that is the scientific name of this plant is Withania somnifera. We obtain the compound withanolite, which acts as anti-asthma and as well as the immunostimulatory, anti-cancer, and also it worked against COVID-19. And Costa Rican frog, from this frog, we obtain quercetoxin, which acts as anti-cancer drug. And then ginkgo biloba plant, which is also called, it is the Tipatiga in Telugu. So we obtain different ginkgolites, which are having lot of applications, which can cure the epilepsy, neurobehavioral problems, etc. And other compounds obtained from the marine resources, cryptophycin, which is the anti-cancer drug, melatonin, also anti-cancer, antibacterial, antivirus, etc. And the Taxol, which is obtained from the plant Taxus brevifolia. This is also anti-cancer drug. And the quercetoxin, just now I have said. So all these, the compounds which are obtained from the plants, marine species, animals, insects, etc., are called natural products. So here my presentation outline is definition, classification of natural products, general structural determination of terpenoids, and general structural determination of alkaloids. And here, what are natural products? Generally, the compounds which are isolated from the living organisms like plants, animals, microorganisms, and marine species. These are called natural products. Generally, these are also called the secondary metabolites. So common classes of natural products are terpenoids, alkaloids, flavonoids, and steroids. So here the compounds which are obtained from the plants, animals, and microorganisms are of two types, primary metabolites and secondary metabolites. So what are the primary metabolites? Primary metabolites are the amino acids, nucleic acids, enzymes, sugars, which are essential for the growth and development and also the cellular functions. And the secondary metabolites are examples, perfumes, colors, pigments, drugs, poisons, etc. So these are for the survival of the species and protection from the predators. So natural products are the compounds isolated from living organisms like plants, animals, microorganisms, and marine species. And then natural products as drugs. There are many natural product drugs, means they are obtained from many of the natural products we get from the plants. So here the best example, morphine, which is a powerful analgesic isolated from the Papaver somniferum. Quinine, an anti-malarial drug, is isolated from the bark of Cinchona succirubra. And vinblastine and Taxol are anti-cancer drugs isolated from Catharanthus rosas and Taxus brevifolia plants. And the next, benzyl penicillin. Benzyl penicillin obtained from the Penicillium chrysogenum. And lovastatin A cholesterol lowering drug is produced from the plant fermentation of Aspergillus terras. Here it is the fungus. So these two are the microorganisms and these three are the plants. So compounds which are obtained from the natural products are which are obtained from the living organisms are called natural products. And here these are the structures of the drug molecules: morphine, and it is the which is the analgesic, and quinine. Quinine is also an alkaloid obtained from the cinchona plant, anti-malarial drug, and the Taxol. This is the structure of the Taxol, and here anti-cancer and benzyl penicillin. This is the structure of benzyl penicillin. It acts as antibiotic. And the terpenes and terpenoids. So what are terpenes and what are terpenoids? Terpenes are a group of compounds, majority of which occur in the plant kingdom. Lower terpenes are generally liquids or low melting solids and have pleasant smell. They are also known as essential oils. These are all obtained from the plants only. So derivatives of terpenes containing oxygen functional groups like hydroxyl, formyl, keto, ether, carboxy are designated as terpenoids. So if you take the limonene, which is having only carbon and hydrogen, this is a terpene. And here OH group is present, that is called the terpineol. So limonene is a terpene, while alpha terpineol and camphor are the terpenoids. So here derivatives of terpenes which are having the oxygen functional groups like hydroxyl, formyl, keto, ether, carboxy, etc. Terpenoids are present in the essential oils like citrus oil, jasmine rose, eucalyptus, lemongrass, etc. And terpenoids are used as medicines and also the perfumes since ancient days. Examples are menthol, camphor, citral, etc. So here the classification of the terpenes. Terpenes have the general formula C5H8 taken n times. N is used as the basis for classification. So N is equal to 2, number of carbon atoms 10. Molecular formula is C10H16 and it belongs to the monoterpenes. N is equal to 3, number of carbon atoms 15. The molecular formula is 15 and H24. This is called sesquic terpene. N is equal to 4, carbon numbers 20 and molecular formula is C20H32. It belongs to diterpene. N is equal to 5. It is sesquiterpene. N is equal to 6, triterpenes. N is equal to 8, tetraterpenes. These are also called the carotenoids. So this is the classification. Depends upon the general formula C5H8N, where N is used for the basis for the classification. And here these are all the examples of terpenes and terpenoids: limonene, alpha pinene. These two are the terpenes: citral, camphor, menthol, alpha terpineol, beta carotene, which is obtained from the carrots. So all these are the examples of the terpenes and terpenoids. And then the important rules in terpenoid chemistry, there are two rules. One is the isoprene rule, which is also called Walsh rule, and the other one is called special isoprene rule. So the skeletal structures of all naturally occurring terpenoids is built up of with the isoprene units. So isoprene is a C5 compound. The IUPAC name of the compound is 2-methyl-1,3-butadiene. So here 1, 2, 3, 4, 5 total number of carbon atoms 5, and there are 2 double bonds. So here 1, 2, 3, 4. This is 2-methyl 1,3-butadiene, which is also called the isoprene. So here, if you take any terpene or the terpenoid, their base skeletal structures are made up of with a number of isoprene units. So like this is one isoprene unit and this is another isoprene unit. And here the special isoprene rule, it gives information about the linkage. The isoprene units in natural terpenoids are joined head to tail, head being the branched end of the isoprene. So here isoprene we can write like this. So this is called the head portion. This is called the head portion and this is called the tail. So now in any terpenoid, generally the tail portion is attached to the head. So this is called head to tail linkage. So two isoprene units joined through head to tail linkage. Here this is the tail and this is the head. Branched, one is the head and this end is called the tail. So these two are joined, head to tail. So these two isoprene units joined like this. So this is the new bond formed between the two isoprene units. So this rule is called special isoprene rule. The isoprene units in natural terpenoids are joined head to tail, head being the branched end of the isoprene. The divisibility into isoprene units and their head to tail union is known as special isoprene rule. And then the coming to the structural determination of alpha terpineol, I'm not going to detailed discussion because I have to cover alkaloids also. So this is the terpene, this is the alpha terpineol. So it is liquid isolated from the pine oil. This is the pine tree and also the turpentine oil. It is optically active, indicating its structure must contain at least one chiral center. So here the chiral center is here. This is the chiral center. And then its molecular formula is C10H18O, showing it is a monoterpene in nature. So from the general formula, we can classify the terpenoids into mono, di, ester, tetra, etc. And now the presence of the OH group is confirmed by reaction with the acetic anhydride. Generally, hydroxy groups, they react, whether it is alcoholic or phenolic, they react with the acetic anhydride to give the alpha terpineol, to give the acetate. So here, alpha terpineol on acetylation, it is giving alpha terpineol acetate. And then the oxidation of alpha terpineol, it is giving a mixture of carboxylic acids, all of which have less number of carbons than alpha terpineol, indicating the hydroxyl group to be tertiary in nature. Generally, primary will give same number of carbon atoms, and the secondary and the tertiary will give generally less number. So based on that, it may be tertiary in nature, and it is also give the unsaturation test with bromine. Generally, if unsaturation is present in a compound, it decolorizes the bromine color, brown color of the bromine. And then the determination of number of rings in alpha terpineol. So here this on bromination, we get the dibromo derivative. So and this OH and bromine, this the general formula here C10H17. This OH and two bromine atoms are replaced by hydrogens. So we get the fully saturated formula. C10H20 in place of OH, one hydrogen, in place of two bromine atoms, two hydrogens. So this is called the fully saturated compound formula, which corresponds to the general formula CnH2n. So this indicates number of cyclic rings present in the alpha terpineol. So this is the important table. So by using the general formulas, we can determine number of rings present in natural products. So fully saturated hydrocarbon of the any terpenoid or the alkaloid, if it gives CnH2n plus 2, that is acyclic compound. So here fully saturated means we have removed all the functional groups, and we have in place of functional groups, we have added hydrogens. Three functional groups are there, OH and two bromine atoms. So three functional groups replaced and we have added three hydrogens. So this is the fully saturated compound formula. This corresponds to general formula CnH2n. N is equal to 10, 2 into 10, 20. So that's why it corresponds to CnH2n. So now CnH2n means that is monocyclic. If you get CnH2n minus 2 bicyclic, CnH2n minus 4 tricyclic, CnH2n minus 6 tetracyclic, like this. And then the size of the ring we can get from the alpha terpineol on concentrated sulfuric acid. We get the paracymene. So here alpha terpineol in the presence of sulfuric acid, para-thymine indicating the alpha terpineol has a 6-membered ring because this is already known compound, and the partial structure of alpha terpineol is this one, 6-membered ring and methyl group and the isopropyl group. Now we are going to establish position of the C double bond C and tertiary alcohol. So we have confirmed presence of double bond by reaction with the bromine, and presence of tertiary hydroxy group on treatment with the acetic anhydride and followed by the oxidation reactions. And then the position we have to confirm, presence we have confirmed, now position. So for that they have done oxidative degradation studies. So terpineol on treatment with potassium permanganate, which is having the OH and double bond. So on oxidation with potassium permanganate, here this double bond undergoes oxidation and we get the dihydroxy compound. So now we are getting trihydroxy. This is already present OH and here 2 hydroxy groups. And this upon oxidation with chromium trioxide in presence of acetic acid, we get ketohydroxy acid, and this undergoes spontaneous lactonization. We get a ketolactone, and this on treatment with again alkaline KMNO4, we are getting a terpineolic acid plus acetic acid, and the terpineolic acid on treatment with potassium permanganate, terebic acid. So based on these reactions, we can get the position of the C double bond C and also the tertiary hydroxy group. Reaction of alpha terpineol with 1% KMNO4 dihydroxylates the olefinic double bond to give trihydroxy compound, and oxidation with chromic acid. So like this, no? So this is possible only when a double bonded carbon atom is having carbon, this C double bond C, one of the double bonded carbon attached to 2 other carbon atoms, then only the C double bond formation takes place. So here oxidation, this is converted into C double bond O, and this is converted into carboxylic group like this, C double bond O, OH. So oxidation with chromic acid cleaves the glycol bond to give ketohydroxy carboxylic acid. The substitution on the double bond should be like this. So the ketohydroxy carboxylic acid suggesting this type of substitution may be present on the double bonded carbon atom. Since the ketohydroxy acid is undergoing spontaneous lactonization, the original OH of alpha terpineol should be gamma R delta position to the double bond, because gamma R delta lactones are readily formed only when COOH and OH are gamma R delta to each other. So lactonization means that is the cyclic ester formation. Right? Normally ketones on oxidation break down to 2 acids with lesser number of carbons. A lactone ring system is stable to oxidation. It is susceptible to hydrolysis. So ketolactone is a methyl ketone. Since its oxidation gives acetic acid, a carboxylic acid, terpineolic acid. So this type of chain may be present because we are getting a ketohydroxy group. So this on oxidation, we are getting a carboxylic acid, and this methyl group is converted into the acetic acid here. And then this is the terpineolic acid, right? This is the ketolactone, and this is the terpineolic acid, and this is the ketohydroxy acid. And then in step 5, in the oxidation of terpineolic acid to terebic acid, CH2COOH is converted to COOH. All the above reactions can be explained if alpha terpineol is assigned the structure. This is the alpha terpineol structure. So tertiary hydroxy group, here carboxylic group, here OH and here OH. Upon oxidation, we get this is converted into carboxylic group, this is converted into ketone. This carboxylic group reacts with the OH and we get the gamma lactone. So gamma lactone formation indicating the presence of the double bond is here. And then oxidative degradation of alpha terpineol we can explain here. See, this is the alpha terpineol, KMNO for oxidation. Here, this double bond is converted into diol. So this is the trihydroxy compound, chromium trioxide in acetic acid. here cleavage takes place. So this is converted into ketone and this is converted into carboxylic group. This is called ketohydroxycarboxylic acid. This upon elimination of water, this OH and OH, alpha, beta, gamma. With respect to carboxylic group, this is the alpha position, this is beta, this is gamma. So OH and H plus from this carboxylic group and OH, acid plus alcohol, we get ester. So like that, internal cyclization is taking place. Internal lactone formation. Okay, alpha, beta, gamma. So this is the gamma lactone. OH and hydrogen eliminated. So we get C double bond O. This is the ketolactone. And this on oxidation with potassium permanganate, here cleavage. So this carbon is converted into carboxylic acid and this will be removed. And this is the terpineolic acid. Again, this on oxidation, here cleavage, here converted into COOH, terebic acid. So all these reactions suggesting the structure for alpha terpineol. And this is the synthesis of alpha terpineol. We can prepare from paramethyl benzoic acid. And this is the sulfonation followed by potassium hydroxide. First, we get the meta sulfonic acid because carboxylic group is meta directing group. After on treatment with KOH, sulfonic acid is converted into OH. This in presence of sodium in ethanol, this ring is reduced. We get the saturated ring. In presence of phosphorus tribromide, OH is replaced by bromine. And this compound in presence of pyridine and pyridine, here dehydrohalogenation, hydrogen from this carbon and halogen from this. So here double bond formation. In presence of ethanol, this carboxylic group forms ester. This compound in presence of methyl magnesium bromide, as we all know, esters on treatment with the 2 moles of methyl magnesium bromide, we get the alcohol, tertiary alcohol. First molecule will be converted into the ketone. Second molecule will be converted into the tertiary alcohol. So in this way, the tertiary alcohol group is introduced. So then the next one is the camphor obtained from the Cinnamon camphora plant. It is also optically active compound having the chiral center. And here the general formula is C10H16O. Camphor has no ethylenic double bonds. And then coming to the alkaloids. So the alkaloids are also the natural products. The word alkaloid is derived from the alkali, like means basic. Due to the presence of nitrogen, almost all the alkaloids are basic in nature. So organic bases isolated from plants are the alkaloids. Alkaloids are natural plant compounds having basic character and containing at least one nitrogen in a heterocyclic ring. So here the examples are morphine, quinine, and this is the piperine. Morphine is obtained from the Papaver somniferum, and the quinine obtained from the cinchona plant, and piperine obtained from the pepper seeds. So alkaloids are generally poisonous, but in small quantities act as medicines. Reserpine, which acts as a hypotensive drug, quinine anti-malarial, ephedrine anti-asthmatic. Alkaloids are found in seeds, roots, leaves, and bark of the plant. Different parts of the plant can produce alkaloids. And here there are some tests to identify the presence of alkaloids in any plant. So generally, a Mayer's reagent, when we take, we can prepare Mayer's reagent, 3.2 grams of potassium iodide dissolved in 60 ml of water, and 1.6 grams of mercury chloride is dissolved in 60 ml of water. Add solution 1 to the solution 2 drop by drop under stirring. The red precipitate gets dissolved and make up to 200 ml to give the Mayer's. So this is the Mayer's reagent preparation. And take a small amount of the compound or an aqueous or alcoholic extract of the plant material in a watch glass and add 2 ml of 2% HCl or sulfuric acid and dissolve. Then add few drops of Mayer's reagent. Yellow curdy PPT is a positive test for the alkaloid. And the drag and drops reagent, this is the bismuth nitrate. So here we get the color white curdy precipitate. If any plant contains alkaloid, it will give positive test white curdy PPT is formed. That indicates positive test for the alkaloid. So here the bismuth nitrate, tartaric acid, and water and potassium iodide. Okay. And the classification of the alkaloids. So alkaloids are classified into 7 groups. So phenylethylamine group, example ephedrine. So this is the phenylethylamine. This is the phenyl ring. This is ethyl group. So phenyl, this is ethyl, and this is amine. Ephedrine is having the phenylethylamine. And the next pyrrolidine group. So example is the hygrine. So this is the pyrrolidine. Reduced form of the pyrrole is called the pyrrolidine. So this is the hygrine, which is having the pyrrolidine. And the next pyridine and piperidine group. So example nicotine which is obtained from the tobacco, piperine from the pepper seeds. So this is the cocaine, which is having this is 5-membered ring, pyridine as well as the piperidine. Both are present, 5-membered and 6-membered. Pyridine is the 6-membered ring containing nitrogen. Piperidine is the reduced pyridine, right? So example is the cocaine. And the quinoline group. So this is the heterocyclic ring, quinoline, which is present in quinine and as well as the cinchonine. And the next one is isoquinoline group, pepaverin. This is obtained from the Papaver somniferum seeds. So this is the isoquinoline group. See, this one is the isoquinoline. So it belongs to isoquinoline group. And the next phenanthrene group, example morphine and codeine. So this is the codeine. So here, this is the phenanthrene. Three 6-membered rings fused in angular manner. So this is called the phenanthrene. So codeine, morphine, they are having this basic skeleton. So these compounds belongs to the phenanthrene group. And the next one is the indole group, vinblastine, lysergic acid, reserpine, yohimbine, etc. or the indole group. So if you take the reserpine, this is obtained from the serpentina plant. Okay, so this is the indole moiety present in reserpine. And here also yohimbine, which is containing the indole moiety. So these are the 7 groups of alkaloids. Alkaloids are classified into 7 groups based on the classification is based on the type of heterocyclic ring present in it. So all nitrogen containing heterocyclic rings are present in alkaloids. And the general methods of structural determination of alkaloids. So first, structural determination of alkaloid involves several steps. First, we should find out the physical constants like melting point, optical rotation, etc. And also the elemental analysis. So it gives what is the percentage of carbon, what is the percentage of hydrogen, nitrogen, etc. From that we get the empirical formula and also the molecular formula. Then identification of the functional groups means nature of the oxygen, nature of the nitrogen, etc. And here what type of oxygen, whether it is alcoholic or phenolic or carboxylic or ketone, aldehyde, like that. And nature of the nitrogen, whether it is primary, secondary or tertiary or acyclic or cyclic, like that. Then identification of the ring system. So whether it is having 5-membered or 6-membered or 7-membered, like that we can identify. Chemical degradation, identification of the degradation products, synthesis of the degradation products also will give the structure. So on chemical degradation like oxidative degradation, hydrolysis, etc., it will give the degraded products. Identification, structural determination of the what do you say, degraded products also will give the final structure of the alkaloid molecule. Then confirmation of structure of the alkaloid by its total synthesis. So these are all the steps involved in structural determination by chemical methods. So if we go to the spectra, directly we get the structural information, but by using chemical methods, these are the steps. And the determination of the molecular formula generally done by the percentage of elements. Just now I have told calculation of empirical formula, percentage of the elements. And then several alkaloids contain oxygen atom. So determination of the nature of the oxygen. The oxygen containing functional groups may be, just now I told, alcoholic, phenolic, carboxylic, carbonyl. In carbonyl, it may be aldehyde or ketone, and methylene group, alkoxy, ethoxy, and then ester, ethyl ester, methyl ester, methylene dioxy. Like this, there are many types of oxygen functional groups. So as usual, tests for the phenolic OH in laboratory, we do know in identifications. Alkaloid is soluble in dilute aqueous sodium hydroxide and reprecipitated by passing CO2. Being a weak acid, selectively precipitates the phenols. So solubility in dilute sodium hydroxide indicating presence of phenolic group, and also the coloration with the ferric chloride is a positive test, and acetylation and also the benzoylation. All these are the tests for the phenolic OH. But here acetylation, benzoylation, also alcoholic OH gives, but the coloration with the ferric chloride is the characteristic reaction of the phenol. And then the tests for the primary, secondary, and tertiary alcoholic group. Primary, secondary, and tertiary alcohols react with acetic anhydride pyridine to give the acetates. So ROH acetic anhydride, we get the acetate. And then this compound, thiocyanate and isothiocyanate, in the presence of triethylamine give the carbamates. And the reaction of alcohols with the 3,5-dinitrobenzyl chloride in pyridine gives the corresponding dinitrobenzoates, which are crystalline solids. So all these are the characteristic reactions. And then how can we differentiate primary, secondary, and tertiary alcohols? By oxidation. Primary alcohols and oxidation give aldehydes or carboxylic acids containing the same number of carbon atoms. Secondary alcohols and oxidation gives the ketones, which on further oxidation give 2 carboxylic acids with lesser number of carbons. And cyclic secondary alcohols gives the ketones, whose further oxidation gives a dicarboxylic acid containing the same number of carbon atoms. Tertiary alcohols and oxidation gives a mixture of carboxylic acids with lesser number of carbon atoms. So this is the primary alcohol, aldehyde and carboxylic acid. Secondary alcohol, ketone and carboxylic acids with lesser number of carbons. And this is the tertiary alcohol, we get the carboxylic acid. And this is the cyclic secondary alcohol, and oxidation we get the ketone, cyclic ketone. This on oxidation we get the dicarboxylic. Here cleavage, and then this is converted into carboxylic group. There is no loss of carboxylic acid. So that is indicating the presence of the cyclic alcohol. And then active hydrogen determination. So presence of ROH, the presence of number of functional groups with active hydrogens, example OH, COOH, NH, etc., estimated by the Jervitnoff method. A compound with OH group is reacted with methyl magnesium iodide and we get the methane. So number of moles of methane evolved is equal to number of active hydrogens present. Not only the ROH, you can take the COOH, NH on treatment with the Grignard reagent. So here number of moles of methane formed is equal to number of active hydrogens present. And tests for the carboxy group. So solubility of the compound in weak acid like sodium bicarbonate with effervescences and liberation of the CO2 is a positive test for the COOH. Compounds with COOH are soluble on ammonia. Carboxy group is esterified by use of alcohol in presence of H+. And the rate of esterification, primary acid undergoes faster esterification than secondary than tertiary. So the number of COOH groups is estimated by titration with standard alkali or by ignition of the silver salt of carboxylic group. The silver is estimated. So carboxylic group on treatment with silver nitrate, we get the silver salt, and also from this silver is estimated. So from this we can know the number of carboxylic groups. Carboxylic acids on heating with calcium oxide undergoes decarboxylation. So by this is called the soda lime. We can remove the carboxylic acid by using the calcium oxide. And the tests for the carbonyls, aldehydes, and ketones. So we can use many reagents like 2,4-DNP, hydroxylamine, semicarbazine, etc. The corresponding compounds are phenyl hydrozones, oximes, semicarbazones. So in laboratory also we do these. And oxidation of aldehydes give carboxylic acids with same number of carbons, while acyclic ketones give two carboxylic acids with lesser number of carbons. Here, oxidation of aldehydes give carboxylic acids with same number of carbons, and acyclic ketones give two carboxylic acids with lesser number of carbons. A methylene adjacent to CO is a reactive and reacts with the nitrous acid to give an oxime. So here C double bond O, if it is present, C active methylene present adjacent to the C double bond O. On treatment with HNO2, we get the nitroso group here. This undergoes rearrangement to give the oxime. So this is the characteristic reaction of the CH2CO moiety. And it is also oxidized by HNO3 to a dicarboxylic acid containing the same number of carbon atoms. And then a COCH3, this is the methyl ketone. It responds to iodoform or bromoform test with iodine or the bromine in alkyl. Then continuation of methoxy and methylene dioxide. All these are the oxygen functional natures, oxygen functional groups which are present in different alkaloids. So methoxy groups, this is also estimated by the G-cells method. In G-cells method, if OCH3 group is present, it is treated with the hydrogen iodide. We get methyl iodide. This iodine reacts with the methyl, hydrogen reacts with OH. So this will become free OH and methyl iodide. Methyl iodide formed can be estimated by using silver nitrate. So we get the silver iodide. Number of moles of silver iodide formed is equal to number of methoxy groups present in the alkaloid. And then reaction with the HNO and then methylene dioxide group are also estimated similarly. Reaction of methylene dioxide group with sulfuric acid releases CH2O, which is reacted with the HI to give the diiodomethane, which on reaction with the silver nitrate, we get the silver iodide. Number of moles of silver iodide is equal to number of this methylene dioxide groups present in the alkaloid. Then the determination of nitrogen, determination of functional nature of the nitrogen. So all the alkaloids, they contain the nitrogen as heterocyclic ring system. Nitrogen is generally a part of the heterocyclic system, or it is in a side chain. So nitrogen may be primary, secondary, or tertiary amine. Already I said, or an amide or amine is identified by reaction with the acetic anhydride. Primary and secondary amines react with acetic anhydride to give acetates. Tertiary amines do not react with the acetic anhydride. So reaction with HNO2, we can differentiate. Aliphatic primary amines react with nitrous acid to give the corresponding alcohols with the loss of nitrogen, while secondary amines give N-nitroso compounds. Aliphatic tertiary amines do not react with the nitrous acid. And reaction with methyl iodide, primary amine requires 3 equivalents of methyl iodide to form the quaternary. Secondary amine requires 2 equivalents of methyl iodide to form quaternary ammonium salt, and tertiary amine requires only 1 mole of methyl iodide to form quaternary ammonium. Also, in this way, we can differentiate primary, secondary, and tertiary amines. And then here are, see, this is the primary amine taking 1, 2, 3 moles to form quaternary ammonium iodide. This is the secondary amine. It is taking 1, 2 moles to form quaternary ammonium iodide. This is the tertiary amine. It is taking 1 mole of methyl iodide to form quaternary ammonium iodide. So in this way, we can differentiate primary, secondary, and tertiary amines. All tertiary amines react with 30% of H2O2 to form the N oxides. So formation of N oxides is also the characteristic reaction of the tertiary amines. and then identification of N-methyl and N-dimethyl groups. So fusion of the alkyl with KOH or soda-lime liberates methylamine from N-methyl group, while N-dimethyl liberates dimethylamine. So Hetzig-Meyer method, which is the most important method, it is similar to Giesel's method. So here also the N-methyl group, if it is present, treated with the hydrogen iodide at 200 to 300 degrees centigrade, this methyl reacts with the iodine, we get the methyl iodide, and this hydrogen attached to nitrogen. So number of moles of methyl iodide formed can be estimated by using silver nitrate. So here number of moles of silver nitrate formed is equal to number of N-methyl groups. This is called the Hetzig-Meyer method. And amide or the lactam group in alkaloid is identified by their hydrolysis with strong acid. So we get the acid plus amide. For example, if we take the piperine on hydrolysis, here cleavage, this is converted into the carboxylic acid, this is converted into the amine. See here, this is carboxylic acid, this is amine. Then coming to the nitro and cyano groups, generally they are absent in alkalides, but chloromycetin, an antibiotic, has a nitro group. This is the chloromycetin. And the next most important determination of the nature of the heterocyclic rings, whether it is 5-membered, 6-membered, or 7-membered heterocyclic rings present by using different methods like Hoffman exhaustive methylation, MDE, and von Braun degradations. So generally carried out to find out the nature of the heterocyclic rings. So nitrogen heterocyclic rings present in the alkalides are cleaved at carbon-nitrogen bond, and the nitrogen is eliminated from the ring. The resulting acyclic segment is identified. So nitrogen containing heterocyclic ring, carbon-nitrogen bond is cleaved, and then the nitrogen is completely removed and resulting compound is identified. Based on that, we can know the heterocyclic aromatic ring. And here, if nitrogen is part of heterocyclic aromatic ring, it is difficult to cleave at carbon-nitrogen bond. The heterocycle is reduced and then cleaved. So these reactions are generally called as degradation reactions. Example, Hoffman exhaustive methylation, MDE, and von Braun degradations. So these three methods are important. Here, this is the HEM, it is also called Hoffman exhaustive methylation. So in this method, for example, if pyridine ring is present, aromatic ring is present, first we should reduce it. By adding hydrogens, we get the reduced pyridine, which is also called the piperidine. And then we should do methylation to convert quaternary ammonium salt. So now this is the secondary amine. It requires 2 moles of methyl iodide. It requires 2 moles of methyl iodide to convert quaternary ammonium iodide. So this compound on treatment with the silver hydroxide, this I minus is replaced by the OH minus. So here we get the quaternary ammonium hydroxide. So this upon heating, water is eliminated like this. Carbon hydrogen bond. With respect to the nitrogen, this is alpha, this is beta carbon. So carbon hydrogen bond migrates here, and this carbon nitrogen bond moves towards positively charged nitrogen. So here what is happening? Cleavage of the carbon nitrogen bond, and here double bond formation. This H plus and OH minus removed as water molecule. So here double bond formation. Here double bond formation. And again, this has become the tertiary amine. If you add 1 mole of methyl iodide followed by silver hydroxide, again we get the quaternary ammonium hydroxide. With respect to this nitrogen, this is alpha carbon, this is beta carbon. So this carbon hydrogen bond migrates here double bond formation. Immediately this carbon nitrogen bond cleaved moves towards positively charged nitrogen. So totally this nitrogen is removed as tertiary amine, trimethyl amine, and we get this acyclic fragment, right? So identify how many carbon atoms? 1, 2, 3, 4, 5. So this is 1,4-pentadiene. 1,4-pentadiene formation indicating that 6-membered ring is present in given alkaloid. So in this way, we can identify the uh, nature of the heterocyclic ring, functional nature of the heterocyclic ring by using Hoffman exhaustive methylation. And the next, if pyrrole ring is present, so if it is saturated, you can do directly. If it is in aromatic in nature or if double bonds, first we should reduce it. So here reduced one, that this is the saturated. Again 2 moles of, because it is a secondary amine, 2 moles of methyl iodide. We get quaternary ammonium iodide in presence of silver hydroxide. This I minus is replaced by OH minus. And then this is the alpha carbon, this is beta carbon. Hydrogen from this carbon is replaced and cleavage of this carbon nitrogen bond. So here double bond formation. Again, 1 mole of methyl iodide, silver hydroxide. You get the quaternary ammonium hydroxide. And with respect to this nitrogen, this is alpha, this is beta. From beta position, carbon hydrogen bond migrated and carbon nitrogen bond cleaved. So totally nitrogen atom is removed as trimethylamine, and here we are getting 1, 2, 3, 4. So 1,3-butadiene is formed. So this is indicating the alkaloid is having the 5-membered ring. And then isoquinoline and quinoline nitrogens undergo only one Hoffman exhaustive methylation. Hem means Hoffman exhaustive methylation only once. The second hem is not possible as the product of first hem does not have the beta hydrogen. Thus, ring nitrogen cannot be cleaved off from the molecule after first hem. So, if we take, this is the heterocyclic ring isoquinoline, right? On treatment with sodium ethanol, this ring is reduced. So now we should convert it into quaternary ammonium hydroxide. So 2 moles of methyl iodide and 2 moles of silver hydroxide. So here quaternary ammonium hydroxide is formed. And then this is with respect to this nitrogen alpha and beta, this carbon hydrogen bond migrates and cleavage of carbon nitrogen bond. So now here only one time. With respect to this, this is alpha and this is beta. Here no beta hydrogen. So that's why only once it undergoes Hoffman exhaustive methylation. And then the quinoline. This is the quinoline. Here reduction. Here also 2 moles of, this is secondary amine. It requires 2 moles of methyl iodide to form quaternary ammonium iodide in presence of silver hydroxide, quaternary ammonium hydroxide. So here with respect to nitrogen alpha beta, so carbon hydrogen bond migrates here, cleavage of this one, right? And here there is no hydrogen on beta position. This is alpha, this is beta. So no hydrogen, that's why only one time it undergoes Hoffman exhaustive methyl. Completely we cannot remove nitrogen from the compound. And then the next method is MD degradation. So Hoffman degradation takes place only when the position beta to nitrogen has hydrogen attached to the carbon. Otherwise, it cannot undergo. Beta hydrogen should be present. But in the MD degradation, quaternary ammonium iodide is reduced in presence of sodium amalgam ethanol. There is a cleavage of carbon nitrogen bond to give a reduction product. So MD degradation may be done before or after one step of Hoffman exhaustive elimination. MD degradation of quinoline. So this is the quinoline in presence of the sodium, in presence of ethanol, sodium and ethanol. So this heterocyclic ring is reduced. In presence of 2 moles of methyl iodide, we get quaternary ammonium iodide. And then this quaternary ammonium iodide reduced with the sodium amalgam in presence of ethanol. This is the MD. Okay, here cleavage. So here this is cleaved, and the next step again hem. This is the MD method. So this is cleaved, and then methyl iodide in presence of the silver hydroxide Here quaternary ammonium iodide, then quaternary ammonium hydroxide. With respect to this nitrogen, this is alpha and this is beta. So carbon hydrogen bond migrates, carbon nitrogen bond towards nitrogen. So this nitrogen is completely removed as trimethylamine, and then this is the, and this is a cyclic segment completely removed. But here we are unable to remove nitrogen from the molecule. So then identification of this compound gives whether the nitrogen is 5-member ring or 6-member ring, we can identify. So then the MD degradation of the isoquinoline, first reduction on treatment with 2 moles of methyl iodide, quaternary ammonium iodide, and then sodium amalgam reduction. So here cleavage, this will be converted into methyl, and this will be converted into tertiary amine. And then HEM means on treatment with methyl iodide followed by silver hydroxide, and then cleavage, carbon hydrogen bond migrates here, and carbon nitrogen bond moves towards nitrogen. This will be removed as trimethylamine, and here nitrogen is completely removed. We get the orthomethyl vinyl benzene. So identification of this compound indicating presence of the 6-membered ring in a given alkaloid. This is the MD degradation. So like this, first we can do the HEM followed by MD, or first MD followed by HEM. In any way we can do. Then the third method is von Braun cyanogen bromine degradation for the tertiary cyclic amines. So cyanogen bromide method is successful with compounds that fail with the HEM. So here this is the cyclic tertiary amine, cyanogen bromide. So here Cn minus, here it takes lone pairs of electrons, and then the bromide ion is associated with this. So nitrogen atom donating lone pair, so it will get positive charge. And treatment with hydrogen bromide. So here cleavage, this bromide attacks here, and this carbon nitrogen bond moves towards nitrogen, so ring opening. And this on hydrolysis, cyano group is converted into carboxylic group. Upon heating, carboxylic group is removed as CO2, and we get the acyclic compound. So formation, after identification of the acyclic compound, we can know the nature of the heterocyclic ring, whether it is 5-membered, 6-membered, like that. And here, this is the N-methyl. Von Braun method, we get this compound, and HEM, we get this one. And the secondary amines on treatment with benzylation. So this hydrogen and chlorine removed, and this CO C6H5 is attached here. And bromination in presence of the phosphorus tribromide. So here polarization, bromide attacks here, polarization, and this OH is also replaced by the bromine. We get the dibromo compound. And then this compound, so this compound here, this bond migrates here, and this bromine attached here, and this bond migrates here, this bromide attached here. So now 1, 2, 3, 4, 5, 1, 5 dibromo pentane, and then this is converted into benzonitrile, C6H5, C triple bond N. So benzonitrile. So formation of 1,5 dibromo compound indicating there is a 6-member nitrogen containing heterocyclic ring present in the alkaloids. So this is about the general structural elucidation or structural determination of alkaloids. And example, and detection of the unsaturation, addition of bromine and HBr dihydroxylation we can do, and oxidation of alkalides with the hydrogen peroxide, ozone, iodine, and or alkaline KMnO4, potassium dichromate, chromium trioxide. All these are the reagents used, and degradative dehydrogenation is done with sulfur, selenium, bromine, hydrogens, etc. And this is the structural determination of papaverine. So papaverine is also obtained from the Papaver somniferum. These are the seeds of the Papaver somniferum. So this is the structure of the papaverine. So these methoxyl groups are identified. Methoxyl groups are identified by the Gisel's method, and then the oxidation will give the oxidative degradation is used to find out the compound. And if you apply the Hoffman exhaustive methylation and MD method, we can know the presence of the uh, six-membered heterocyclic compound, etc. So this is the papaverine isolated from the Papaver somniferum seeds, right? So this is the structure. So methoxyl groups can be identified by the Gisel's method. Okay, thank you. I'll stop here. Any doubts? Anything you'd like to discuss?